INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altair Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksa International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka. With its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them: INSEE Sunstar, INSEE Mahavalley Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Convert by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
Sri Lankan cement manufacturers and concrete manufacturers, and 10% are international guests from 8 countries in Sri Lanka, Switzerland, Germany, Bangladesh, Thailand, Indonesia, India, and Vietnam. So I think it's a great opportunity to have such an international webinar for the benefit of Sri Lanka, but also even other countries. And I wish all of you a really lively and interesting session. INSEE Cement will continue to invest into research, development, sustainability, and is your solution partner going forward. I'm looking forward to a really lively webinar with a good and high quality Q&A session at the end. In case any question won't be answered or needs much more detail, please put it into the chat function with your email and phone number, and we will revert back. Otherwise, send me an email, jen.kunik@siamcitycement.com. And for any technical glitches, as it's our first webinar, I apologize. As always, we will improve while we go along, and I'm sure in case there happens anything next time, it won't happen. Again, thanks to all for your support, for the great improvements we have done together over the last 2 years, for the drive and the passion, and let us build for life, let us build Sri Lanka, let us build the nation. So please enjoy the session. Thank you very much, and I'll hand over to Gayani again.
Thank you, Jan. I would like to introduce our speaker for today's webinar session. He is none other than Dr. Moussa Baalbaki, Head of Product and Solution Portfolio of INSEE Cement. Dr. Baalbaki holds a PhD in Civil Engineering from Sherbrooke University in Canada on the influence of the cement superplasticizer interaction on concrete properties. He started his professional career in 1989 as a research engineer for the Industrial Chair on Concrete Technology and the Network Center of Excellence on High Performance Concrete in Canada. In 1998, he joined Corporate Housing Group Support in Switzerland and held several positions until 2017 in the areas of R&D, open innovation, advanced concrete technology, and technology transfer. Dr. Baalbaki joined INSEE Cement in Jan 2018 as a head of products and solutions portfolio. He has a large experience with customer needs and different construction application segments on concrete technology and constitutes, from production to product application, coupled with holistic version on cement, aggregates, and industrial technology. May I now invite Dr. Baalbaki to give your presentation.
Okay. Good afternoon, everybody. It's really my great pleasure, great pleasure to connect again to all my colleagues, my friends in Sri Lanka. Probably most of you know I'm sitting now close to Zurich, between Zurich and Basel in Switzerland. And I'm really happy to have this possibility to reconnect with you. Hope you are all fine with your respective family. Therefore, it's really, again, my great pleasure to have this opportunity again. And thank you for your full commitment. I see the big crowd to participate to this somehow knowledge sharing session. As Jan well mentioned it, we do not stop innovation. Therefore, we want to stay connected. We are committed to organize such a knowledge sharing session every month. Therefore, this time will be on a virtual way. The topic for today, as it was presented, is overview of international standards on performance-based specification. And the agenda I will go through is really to talk first about the context with sustainable performance solution, because it's all about really sustainable performance solution. This is a long journey, and as we already mentioned it 2 years back, that we never will be able to be successful without you. Therefore, we have to go together, take it together, this journey. If I would like to put some context, important context, to go through the cement constituent and property, because when we talk about standard on cement, it is important to all of us, as this topic will be covering two big international standards. I would like that we all of us understand in the same way what is cement, its constituent, and the properties, because this is really the basic of really understanding the standards. And after that, I will cover international cement standard, the ISTM, and the BSEN 197 before concluding. Therefore, just to start my presentation in terms of context, I have been already discussed this slide regarding what are the mega trends that will really drive societal need for sustainable construction. Here we have population growth. Today we are around 7.5 billion. We have more and more megacities. Therefore, these are what we call our reality and what are our implications. Therefore, when we talk megacities, very often people think we go only vertically. No, we go vertically, we go even deep, we go horizontally. Therefore, there are a lot of challenges. And out of those challenges, we see that there are 3 mega trends that are important to look at. Our first of them is a solution for sustainable construction. You will see, I will give you some overview about what has been said before in terms of where are the challenges, where are the topics we have discussed. Carbon footprint and material scarcity are key. Okay, this is really important to take into consideration. We have the digital transformation where connectivity, where smart cities are taking more and more in place, and better living standard with more efficient technology. For example, when you talk about digital transformation, this is, for example, an example of in Berlin, in Germany, a self-driving public bus, fully electrical. And I would like to say, for example, in UK in 2030, no more even hybrid car will be accepted. No more petrol, no more diesel, no more even hybrid. We have to go 100% electrical. And when we talk about better living standards, you see the example from our legacy horse in Indonesia, where Jan was there. It's an indoor climate solution for concrete thermal activation. And for that, of course, we need right standards, we need technology, but we need innovation. This is why when we look to all these trends, there is a huge opportunity for Sri Lanka to grow and innovate in sustainable and efficient solution. And if we look in terms of solution for sustainable construction, we have been somehow discussing together several somehow knowledge sharing in our knowledge sharing space topics. We have run more than 14, 16 topics, and first, for example, we start with Professor Nanayakara, who have introduced the concept of durability for mass concrete. Okay, he explained us in a very holistic way where are the measures, where are the precautions to take when you talk about mass concrete. After that, I have introduced sustainability performing concrete, especially on the high performance part. After that, Professor Ranjit Disanayake from Pera University, he discussed about the importance of sustainability construction for Sri Lanka. Therefore, we set the ground and discussing after that more in detail on high strength, high performance concrete with engineer Fernando, from managing director of civil engineering consultant. After engineer Marit Mendes from Mendes Cobin Consultant, he discussed about the FIDI guidelines for construction project management. I say the critical path for successful project management. Tushara, Dr. Tushara from Open University. When we talk about sustainability, of course, we talk about very often low CO2 footprint product, but now we can go even beyond conventional mineral components. What you call somehow products that are really that can replace the conventional, that go beyond this normal mineral component. He discussed about high performance concrete is novel mineral cement additive. For performance-based structural design on the Eurocode, Professor Pradid, he gave us a very good insight about Eurocode with performance-based structural design. Now, investigation of failure, because very often when we don't fulfill service life, we can have some failure. I will discuss about two failures just in a couple of minutes. Forensic engineering was presented by Professor Ranjit Disanayake from Pera University. And after that, we have followed with design and construction experience in mega project that was with engineer Alvis, where we look at after all steps important when designing and constructing a mega project, okay? And you see in Sri Lanka, we have a lot of mega projects on the pipeline. Now, the topic number 10 is about managing construction timeline with engineer Budi Satsara from Sanken Construction. He discussed about really managing construction timeline. This is one of the key success factors, you know, for somehow managing such a project. After Professor Harsha from RUNU, he discussed about repair, retrofitting on structural element. We had the design of shear critical reinforced concrete with Dr. Kushan from Pera University. Regarding the scarcity, we discussed a lot about I say scarcity of raw material, especially from the aggregate side. I have shared my experience with manufactured cement as alternative to river cement. I have two slides to give you about this topic. A novel technique for concrete road. We have a lot of concrete road coming, I-road, a lot of big project coming in Sri Lanka. Therefore, Professor Vasanta for University of Moratuwa, he has really generously somehow present us the future advantage benefit of designing a road, concrete road. And the last interesting presentation came from University of Melbourne with Professor Brian Mendes, where Professor Brian Mendes discussed about modern concrete technology transforming waste materials. Therefore, what is about circular economy, end of life of material. Therefore, there also, it was a very good open eye for a country like Sri Lanka, where we can somehow have full opportunity to move to this direction. Having said that, when it comes, for example, to the topic of forensic, I have just somehow here a slide because we talk about a lot about concrete. You know, today concrete is almost per capita. We have a cubic meter, for we can say 2019, we have put almost 7 to 8 billion cubic meter of concrete. That is huge. Concrete is a universal construction material. It has a lot of benefit, but at the same time, it could be really a possible universal construction problem. First example, I would say, come from Italy. I mean, you have all heard about this bridge collapsing, the Morandi Bridge, who is only 55 years old bridge, and with 43 people were killed, okay, on this bridge. That was on August 2018. And unfortunately, again, this happened just beginning of this month, just less than 4 weeks ago. Again, another bridge, 50 years old. It's a 300-meter bridge that collapsed in Aula. And another tragedy could have happened. The bridge was deserted due to coronavirus containment measure. Therefore, I would say otherwise, this is a highly congested bridge during peak hours, and that could be another tragedy. Therefore, when we look to these two bridges, and when we look to somehow the map, you see, I show here the map of Italy. You see, these two bridges are very close to the Mediterranean Sea, and those bridges can be suffering a lot from exposure condition due to marine structure. Therefore, they will see already for the first one from the old Morandi Bridge that collapsed in Genoa. Corrosion was one of the main reasons. Therefore, it's really important when we design those bridges to take into consideration not only the prescriptive way, it means somehow the structural requirement, but we have to take also into consideration other parameters related to exposure condition. Okay, therefore that is really important. And this is why the next session I will go more in deep on the designing concrete based on performance. Okay. Therefore, this shows clearly that it is really important, that standards are really important, that we should not go for racing for a number of megapascal, because there are other engineering properties today that need to be taken into consideration to assure that we don't come with such a tragedy. And when we look, for example, today state-of-the-art technology with projects all around the world, we have seen that a lot of subjective concepts from performance, when we were discussing about low permeability, when we were discussing about high strength, when we were discussing about somehow chloride-resistant concrete, okay, that allow a designer to design according to required services have been applied, okay? For example, this slide you see that, for example, Burj Khalifa, tallest building. When we look to the North Sea of Europe, deepest, longest, for example, bridges linking the Hong Kong, Macau to the mainland of China, a 55-kilometer long bridge exposed to marine structure. All this mega infrastructure project has been designed based on durability indicators for sustainable performing approach. Therefore, thanks to somehow innovative standards that allow somehow to go further, push further the envelope, moving from a purely prescriptive to performance based. Therefore, prescriptively, this is exactly the topic I would like to, I will discuss next time, is from the prescriptive point of view. Okay, very often pre-qualification are mainly done on cube. Okay, therefore, even though according to the concrete standard, if I take the EN 206, okay, identify exposure condition very often is minimum cement content, maximum water cement ratio. Even though when we talk about permeability, there is no consensus of that. Therefore, very often is pre-qualification are done on compressive strengths, okay, as you can see on job site, and you get compliance. And if you do not fulfill, you go for repair. Therefore, when you move to a performance base, very important first is to understand what we call the deterioration mode. It's very important, transfer mechanism, what could happen, okay, to any object, concrete bridge or a balcony of your house, you know, what kind of deterioration mode, and out of that you define durability indicators. Okay, are we going to have a corrosion to the carbonation? What kind of indicators that are to be integrated now to the mixed design? And the pre-qualification tests are not done only on tube, but also on others indicators. And those indicators are introduced to service life modeling. Okay, therefore, this is really the approach that is used, okay, to assure that the expected service life of your design object will fulfill the needs. Now, of course, specifier and suppliers, okay, they have faced challenges in translating this long-term durability requirement into a specification for laboratory testing. You will see, I will introduce you for those who had no chance still to come and visit us to our new I2I Innovation to Industry Collaboration Space. Therefore, this is, I will come in a couple of minutes about it. And at the same time, when it comes to scarcity of raw material, we have discussed about these topics just about 2-3 months ago, that very often what we call manufactured sand, these are not purpose-made product, okay? They are really crushed fines or quarry dust, okay, compared to natural sand. If we look to those products, very often they have very high amount of fines, very also inconsistency, can go from 5 to 20% on what is passing the 75 micron. And at the same time, when it comes to their shape, as they are crushed, okay, they don't have favorable shape. Therefore, we have developed and we present it to most of you really a very holistic approach how to tackle with different indicators, quality indicators, to achieve performance, for example, in terms of flow, compressive strengths, okay, using those products. Therefore, all that has been introduced in our I2I. Therefore, we were proudly happy, you know, together with all of you, most of you, to open this collaboration space October 31st of 2019, just a couple of months ago. And this is really to engage a very effective collaboration driven by openness. When we say openness, of course, we want to do it with all opinion leader, all stakeholders, including cross-industry, including with our competitor, because with our competitor, we can work a lot on what we call a pre-competitive project. And I'm so happy to hear that today, even though we have some registration from our colleague from the cement industry in Sri Lanka, I'm really glad and very thankful for those people who came and who show this commitment to openly collaborate together. The speed, when I talk about speed, you will see that very often, you know, it costs a lot to our country. In Sri Lanka, it costs a lot to send some time to UK, to Singapore, to places to get certificate, to get approved some performance of product, okay, for some project. And all this has been introduced in Sri Lanka. And when we talk about connectivity, is now, I would say, we just don't do it through a face-to-face discussion or through really a technical paper, okay, but we do it directly to not a virtual, but to a very concrete space, a collaboration space, okay, where all together we can develop efficient, sustainable solution for Sri Lanka. And that is really, I would say, what we really are committed for. And this is what Jan just said it during the introduction, that at INSEE we are really committed for that. We are really committed for that. Therefore, for the I2I, you see, we do not have what we normally have in a normal concrete lab, okay, because this lab is not a technical customer support lab. Therefore, we are moving from the concept of supporting customer more to performance collaboration based, okay? Therefore, solution is not only developed by us, it is developed together with our customer, okay? With our collaborator. Therefore, we have spaces like durability spaces, like chemistry, rheology spaces, aggregate spaces, strength testing and wet spaces. All this, we have introduced what we call state-of-the-art equipment tools that industry today is used. Okay, for example, for Burj Khalifa, we were discussing was pumping concrete. They were not designing concrete based on a slump test. They use rheometer, for example. Okay, when porosity has been, we are building with porosity with some solution. They are based on tests on durability related to corrosion. Okay, therefore, all these are really important to take into consideration that what we will see in those functional spaces will really support development on standards, because they are coming from the standards. These are coming from academia. These are coming from really huge effort that was made by academia, okay, to make the proof of concept of service life modeling that yes, today we can go beyond the 50 years design, okay, service life design. Therefore, for that, I come now to the next topic of my presentation about cement constituent and property before we come to the core of the standards. Because I would like that we all somehow have what we call understand, when I say the basic, because very often in terms of terminology, you know, I can call something mineral components, another person can call it supplementary cementitious materials, you know, that is very good that all of us will understand what means cement, what are the constituents of cement. And I will also take the opportunity here to give you some properties that are taken in most of the standard when it comes to clinker, when it comes to mineral components. Okay, therefore, cement constituent, okay, we all know very well that clinker is the basic. When we talk about cement, is the most relevant, what I call a cement constituent, because it's the real mineral activators. Okay, that is very important, clinker. After that, with clinker, we have to add what we call gypsum to regulate some phases in the clinker, and this is what we call ordinary Portland cement. Of course, we can have minor addition up to 5%, okay? But this is our ordinary Portland cement, and this is covered by our standard, the SLS 107. Okay, now, if we add to these two constituents what we call mineral components, now what we have what we call composite cements. I use international somehow vocabulary, but in Sri Lanka we will call it a blended hydraulic or Portland limestone cement. The blended hydraulic will be the SLS 1247 and the SLS 1253 will be Portland limestone cement. Therefore, we have in Sri Lanka the coexistence of these three standards, okay? Now, to go more in deep on the clinker phase, for example, we need raw material to produce clinker. And as you know, in Sri Lanka, we have only one facility to produce clinker, is in Putlam, okay, owned by INSE. Therefore, for that one, we need raw material. These are the oxide, the oxide like calcium, ferrite, silicate, or aluminum, okay? And here you have the most commonly sources. For example, for the calcite, we use calcite, calcium, we use calcite, we use limestone, we can use marl, you can use shale. For the iron, mainly will come from the clay, with the clay or iron ore, okay, or mill scale. These are in some places. Silicate will come from clay, will come from marl, will come from sand, okay. And the aluminum will come from clay, mainly from shale, or sometimes from also some byproduct. Therefore, with all this material, what we call the raw materials, we produce raw meal. And those raw meal, they go to kind of like kiln, okay? Therefore, in the kiln, we have like two important parts of the kiln. We have the preheater, okay, and we have the core of the kiln. Therefore, in the preheater, what we do is when you look the proportion by weight, we put the raw meal here, okay, and we start to heat, okay, and dry and prehydrate it. Therefore, if you look the temperature profile, we can go up to 600 degrees, okay, and mainly you see that the calcium carbonate, the limestone, is the main constituent of the raw materials, okay? Therefore, after that, when the first step is finished, the raw meal will go to what we call the calcination zone. And there, the temperature can go up to 1000 degrees C. And this is where the calcium carbonate will be transformed to calcium oxide and emission of CO2. And this is where when we say production of clinker, okay, it has a very high CO2 footprint, because for every ton of clinker, we all know now that we are producing approximately, depending to process we use, approximately half, I say 0.8 to 1 ton of CO2. Okay, we can say equivalent to 1 ton. For every ton of clinker is the same ton of CO2. Okay, therefore, if I go to OPC, for example, for every kilogram of cement is the same kilogram of CO2. Therefore, after that, the calcination zone, it will go to what we call a transition zone, where we start to form the nodules, the clinker nodules, okay? We have agglomeration, the temperature go up to 1200, and from there, you see that most of the free lime will combine with the C2S that we call the belite, I will come to that later, to form what we call C3S, okay? And these are, we see at the end, the 4 main constituents of the clinker that I will discuss about it. They are the silicate phase and the aluminate phase, C3S, C2S, C4F, and C3A. And after that, we come to the cooling. Therefore, we have to quench very fast the clinker, okay, to keep its reactivities. Therefore, this is really, this transformation will take about, let's say, 1 hour, and we can produce, for example, one of the largest kiln in the world is owned by our group in Saraburi, up to 10,000 ton per hour. Okay, therefore this is, for example, in Putna we can go up to 800 to 900,000 ton of clinker per year. This is our production capacity. Okay, that is important that we know when we come to standards, when we talk about clinker. This is how clinker is produced, okay? Therefore, now when clinker come to composition with cement, okay, we see that the four main phases are silicate phases, therefore alite and belite, mainly composed by C3S, and what we call from the liquid phase, we have the aluminate somehow component are C4F and C3A. Here again, when it comes to standard, they have a certain, there is some specification to fulfill when it comes to a specification for some type of product. And we add, of course, calcium sulfate, mainly we call it gypsum, okay? People know it as a gypsum, okay, to regulate mainly the C3A. And of course, you have some minor element of alkali sulfate, some MgO, okay, somehow sodium, potassium, okay. Therefore, this free lime, this all can be also as we call them as minor addition. Therefore, now when we take this now cement, okay, that we have produced out of the clinker with the gypsum, okay, and we put it with water, we have reaction called hydration. Okay, now, if I look now from the different constituents of clinker, what is important, okay, that we all see that the silicate phase will be responsible more than 60% on the hydrated product of calcium silicate hydrate. And you will see later, this is exactly what gives every single performance or every single megapascal we achieve at the end when we produce concrete. And we have what we call portlandite, okay, portlandite or calcium hydroxide. And when you look to this scanning electron microscope, put it here that you have a certain idea about the scales, because very often we talk about porosity. What means porosity? Okay, you see the scales here, we have 10 micron. When we talk about calcium silicate hydrate, okay, compared to portlandite, okay, where this is really, you will see later, is the weakness of concrete, is exactly like in concrete. When we talk concrete, the smallest particle in concrete is cement, is about, let's say, 20 micron, 10 micron, okay? And the biggest particle is aggregate is 20,000 micron. 20,000 micron. Therefore, this big gap, okay, will challenge concrete technologies, okay, to achieve a maximum capacity. Okay, and for that we need to fulfill right grading. This is why when it comes to concrete technology, concrete mix design, why aggregate, okay, are not inert, but they are key indicator or key parameters, okay, to achieve the best compressive strength, okay, the best compacted concrete. It's the same when we come to cement, okay, we need to have as much as possible particles, okay, to somehow densify this microstructure of the cement paste, okay. Therefore, if we can take out such a big, okay, calcium hydroxide, okay, we can really refine the microstructure and achieve more dense, okay, microstructure. Now, when it comes to aluminate, okay, the aluminate, okay, need to be regulated with calcium sulfate. Otherwise, you have what we call problem with stiffening, okay, or problem with sometimes falset or falset. This is really coming from a non-well-regulated C3A. Therefore, the main product is ethylene, okay, and ethylene is just after a few seconds. It's a very important cement hydrated product, okay, because the ethylene, okay, will control later the right dissolution, okay, of all the ion we need to start, okay, to precipitate and keep the hydration in a normal way to pursue its development. Otherwise, if we don't form ethylene, we will form some calcium aluminate hydrate, and this will stop some dissolution. This is why when we produce your own cement, when you produce it, you can do some optimization that I will show you later why it is very important to optimize this couple between C3A and calcium sulfate. And a couple of hours or days later, this 3-sulfur aluminate ethylene will transform to monosulfur aluminate. That will be most of the last product you find in your concrete. But one important thing, at the first knowledge sharing session, Professor Nanayakara was talking about mass concrete. Okay, and in mass concrete, we can have a problem if we don't control the temperature of mass concrete. Okay, we can stop the formation of ethylene at early age and we form what you call delay ethylene formation. Therefore, we form monosulfur aluminate instead of ethylene, and later on with age, after 1 year, after 2 years, okay, this monosulfur will again go back and form 3-sulfur. And you see, these are very long needles. They will, exert huge tension in the concrete, and this very high tensile stress, okay, will develop cracks in your concrete. And this is why we call it delay ethylene formation in mass concrete. So it's very important, okay, to control when you go to mass concreting, okay, to control the aspect of heat development, okay. And this is why I will come later. The heat is coming from where? This is why when it comes to standards and we talk about low heat cement, how we can achieve low heat cement, in which kind of product design, okay, low heat cement can be achieved. Now, calcium sulfate, here again, it's important when we come to constituent of calcium sulfate. Calcium sulfate can come from a natural occurrence like anhydrite or gypsum, okay? This you find it in the nature, okay? And they are really present in almost all continents, okay? And these are really a product that we use during cement production, as I said, to regulate the C3. But also we have alternative to this natural occurrence, because we talk about sustainable development, we talk about circular economy, therefore how I can take valuable, okay, byproduct and turn it to value, okay, to our industry. Therefore, very often we can see also some artificial sources, what we call FGD gypsum, obtained by a flue gas desulfurization system, okay. The flue gas desulfurization system is that the sulfur is removed, okay, from the flue gas, for example, with the help of lime, okay, and the chemical of this FDG gypsum is very identical to natural gypsum, okay. but usually even greater impurity, Therefore, FDG, I would say, gypsum for modern power plant can completely replace natural gypsum in almost all applications. Okay. Also, we have what we call phosphogypsum. This is a byproduct from fertilizer industry, where we, for the production of phosphoric acid as a fertilizer, we treat phosphate ore, okay, with sulfuric acid. Therefore, we produce through, after this, I will not discuss this relation, phosphogypsum. Okay, I mean, the main challenges we have here, we at INSEE, we look very much to that, because very often they have some radioactivity element, okay? Therefore, I'm not saying that all of them, but it's very important that we look after this important somehow issue that can that phosphogypsum can bring, you know, to the use of this type of I say gypsum to cement production. And also we know very well that calcium sulfate are also used for plaster, mortar, like a plaster of Paris, you know, for wall board, for ornamental stone. And there is a lot of application of gypsum, of calcium sulfate for this segment. Now, when I was discussing about calcium optimization, you know, when we optimize gypsum, this is why it's very, very important, you know, when you get a finished product. Okay, when you get a finished product, this you cannot do it, you know. But if you produce your own product, okay, if you produce your own product, you can optimize the gypsum, okay, because as I say, gypsum play a very important role, not only on regulating the citrate, but also on regulating the dissolution rate, okay, during the dormant period of different spices that need to grow in the solution and come topochemically to the surface of the cement grain to develop the hydrated product. Therefore, you can see here, for example, at a different age from 1 day to 28 days, these are the compressive strengths, okay? And you have, for example, optimization with different SO3 content, different gypsum content, and you see that sometimes you have optimum for the 1 day, okay? Then when it comes to 28 days, okay, if we, for example, want to achieve high late strengths, okay, probably the optimum will be a trade-off between the early and the late strengths, okay? But if we don't put enough sulfate, this could be okay for the 1 day strength, but you see the problem we have at 28 days is that because we start to produce what I call calcium aluminate hydrate, we don't have enough ethylene, and these are blocking. These are very strong retarder, let's put it like that, okay? They are somehow blocking the solution, okay, of the different spices from the clinker to the solution that later on it pay off, okay, in the compressive strength. This is why gypsum optimization are very important, and you will see it in the standard when you come to the standards, okay? When we move from a prescriptive to a performance-based, now standard allow that you don't have to fulfill the prescriptive way, let's say 3%, 4%, if you prove, okay, from a mortar test, expansion test, okay, that you fulfill the requirements, okay? That is the performance base. Now, hydration. I mean, hydration is very important because at the end of the day, okay, cement is hydrated in concrete, you know, and it's a very simple material when we talk about cement, but at the same time, when we look all the reaction that happen is quite complex, okay? Therefore, this simple material is very complex reaction, okay? Need to be, need to be understand, okay? In order to fully take advantage, okay, of great product, okay, with great technology to achieve great performance. Now, when it comes to hydration, what we do first, we have your cement, you have your water, okay? Therefore, over the time when you mix them, you produce what we call a hydrated cement paste. And you have a certain, let's say, porosity. This is a water, okay? When this water will dry up, you will have a certain porosity. But within the cement hydrated phase, you have pores. This is small pores. But you have what you call the gel pores, and those pores will have part of the water that is chemically, structurally bound. Like when you talk about calcium silicate hydrate, 3-calcium aluminate hydrate, okay, calcium hydroxide, okay, you have water that is chemically bound, okay, these are the gel pores. But you have capillarity pores, where the water is not chemically bound, it is only physically bound. Therefore, in some hydrometric condition, in terms of relative humidity or temperature, we can lose this water, and this is why you have what we call volumetric change, and this implies shrinkage. This implies shrinkage. This is very important that we understand at this level that the cement hydration is an important link, a really important link to concrete performance. Okay, we need to master, we need to understand the basic of that. Now, this is why I come now when it comes to standards. Why we have, for example, type 1, why we have type 2, why we have low heat cement, why we have sulfate resistant cement, there is reason for that. Because why sometimes we have some limitation, okay, why we need to further develop innovation, development, okay, to have solution, okay, from the somehow the cost optimization ways is feasible, okay, that we can bring to the market, but at the same time it can fulfill, okay, construction needs. Now, when I look the progress of hydration, okay, in terms of hydration, the hydratic kinetic, you see, the first 3 big elements, and as hydration is exothermic, develop heat. Therefore, you see at a very early age, most of the heat will come from aluminate phases, especially C3A, and after that 10 hours to 1 day from the C3S. Therefore, automatically when you look to that, you all agree with me now that we need to limit the amount of C3A, the amount of C3S when we are talking about OPC, OPC based. And you will come, for example, I will show you how, for example, the ASTM, they have a type of cement, okay, that is for low heat cement. And you will see where are the specifications when it comes to C3S and C3A. Okay, and for long-term strengths, we know that the C2S, okay, that produce the same hydrated product than C3S, okay, will not contribute at early age strengths or maturity. It's mainly coming from the C3S. This is why we need to have the right optimum mix in order to fulfill some application requirement. After that, we come, for example, to the concrete side. Therefore, you see, you have here, from the fresh concrete, you go to hardened concrete. The aggregate sand, stay aggregate sand in the microstructure, okay? You have an interfacial zone of transition between the hydrated cement base and the aggregates, okay? Now, you have the water-filled pores, okay? And those water-filled pores will depend very much, okay, to the water demand. Now, if you look, for example, to the right graphic here, what I have here, you have the estimated chemically water-bound, and you have here the water-cement ratio. Therefore, you see that if I want to chemically bound my water with all the cement hydrate, therefore fully hydrate my cement, okay, I need approximately 0.3 to 0.35 water-cement ratio. In this case, I will almost not have any water-filled pores, therefore no more porosity, okay, or a little bit of porosity. Therefore, I will have a very dense microstructure where most of the pores are gel pores because they have fully participated, okay, during hydration, okay, where the water is chemically bound. But in reality, okay, when we look most of our application, we are above this water-cement ratio. And this is what I call the workable water, water that we adjust to give us the possibility to mix and place the concrete. Okay, and this will change a lot, will be very different from segment to segment, okay, in the application. When I look to the industrial segment, where more super-plasticized or more rational concrete production and delivery, we go more toward 0.4 and below. Okay, but when you go more to the retail or to a grade of concrete that are below 30, okay, water cementation should go more above 0.6 and above. Therefore, that is why at the end of the day, when you look to the microstructure of such a concrete, okay, to the concrete, okay, it will be very different, not because, okay, your OPC, okay, has somehow developed a different product. No, you develop always same product. You develop calcium silicate hydrate, you develop calcium hydroxide, okay, you develop trisulfur monosulfur aluminate, but the difference is that in terms of porosity, depending on water cement ratio, depending on capacity, depending on other parameters that I will come just in a couple of segments, how now I can, this is a scanning microscope of a concrete cement hydrate paste, okay? Therefore, you see that we still have, even we fully hydrate our cement paste, we still have a lot of porosity. Therefore, that is the question here. Sometimes, two concrete having the same compressive strength, one will be more permeable than another one, okay? Just because it's a porosity. And when you talk about porosity, I'm not talking about 1 millimeter, because when we look, for example, calcium silicate hydrate, and we talk about the size, we are below 50 nanometer. We are below 50 nanometers. Therefore, if you produce your concrete and you redefine your microstructure and have less than 50 micrometer in terms of porosity, you have a very dense concrete. And when you go above 50 micrometer, okay, now you start to have more of this open porosity. And this is where some challenging in terms of durability can happen, okay? Therefore, prescriptively, it's very difficult to assess this. Therefore, we need to go to a performance base. Therefore, this is why when it comes to cement constituent now, there is, if we add to OPC, okay, mineral components, we end up, okay, we have a series of products called composite cement, okay? Therefore, we can call them, as I said, blended cement, blended hydraulic cement, different names are given, okay? But generally speaking, we talk about composite cement, okay? And those composite cement, they have some feature advantage and benefit when it comes to the how we can complement the hydration reaction, okay, and providing to the microstructure of concrete, and this is all in standards, okay, a refinement of the microstructure, okay. Therefore, it's like I have a sand with a certain grading, and I miss fines, and if I miss fines, okay, I have very coarse, therefore I can have no bleeding, okay. What I can do, okay, how I can close this gap. This is exactly when it comes to microstructure, very often is not only chemical, but it's physical, it's physico-chemical effect when it comes to refinement of the microstructure. Now, those mineral components, I would say the most classical one, okay, are granulated dust furnace slag. We are talking about the fly ash, we are talking about natural pozzolan, we are talking about limestone or other fillers. Okay, now how we classify them? I would say, let's do it easy, okay, in terms of reactivity. When we start, for example, with slag. Okay, slag, this is a byproduct from pig iron, okay, pig iron industry. And the pig iron industry is a raw material for steel industry. Is that I produce clinker, is a raw material for producing OPC or composite cement, the same. Therefore, pig iron, by producing pig iron in furnace, you produce blast furnace slag. And those blast furnace slag, they have a basicity very often above 1. And this is why we call them not pozzolanic material, but latent hydraulic material. Because those products, if we mix them with water only, just I take slag, I mix it with water to a certain fineness, of course, grind it. After a certain time, I will develop exactly the same hydrated product than clinker, than OPC. Therefore, this is why we call them latent hydraulic. And we can achieve, okay, some more performance by adding some activator, what you call accelerator for hydration. For example, byproduct from the hydration reaction of clinker is calcium hydroxide. Now, you have two other products called pozzolanic materials. And those pozzolanic materials, you have the technical one, byproduct like fly ash, coming from power plant. We have in Sri Lanka, in Morochedi, for example. And those fly ash, they do not hydrate in presence of water. Therefore, they are inert. If I use them with water, they are inert. Okay? Therefore, they need an activators. Okay? Some activators work very well with them is like lime. Therefore, lime is a byproduct from the hydration reaction of clinker, portlandite. Therefore, if you put lime with this product, you will develop strengths. And this is what our ancestors have done during Greek time, during Egyptian time. Okay? If you look how we have built the Pantheon, how we have built pyramid, technology is just like that. Okay? They take aluminum silicate, activate it with lime, hydrated lime, and they get strengths. Okay? Now, you have also natural sources. Okay? This can be volcanic or sedimentary, okay, rocks. The same, okay, they need to be activated. As this, we put them under pozzolanic materials, okay? And last but not least, you have fillers like limestone, okay? I mean, we call them cedars. We call them cedars because they have a very important role, because when you grind those materials, okay, in terms of packing density, if I take a cement, a blend, let's say 3,500 blend is the finest, how fine it is. Those materials can have double the fineness, can go up to 6,000 blend. Therefore, they have a seeding effect. Therefore, they help, okay, all the hydrated product to link together, like they bridge them. And on top of that, if we take limestone will react with aluminate to form what we call monocarboaluminate. And this is why when you take limestone cement, you can develop 42.5, even 42.5 R like our sandstone, just because you integrate the technology physically and chemically, okay, to develop such a product. Therefore, these are the main products. Now, of course, when it comes to standards, there are key indicators. Yes, there is key indicators. Therefore, we know, for example, for the slag, we need to control basicity, the glass content, very important. For example, slag, we have our internal product specification, more than 90% of glass content, aluminum content, titanium oxide. These are all quality indicators, okay? They are somehow mandatory sometimes, or they are optional, okay? This is really important to take into consideration. After that, for the fly, for example, fineness, when it comes about glass content, about alloy and bird carbon, when it comes about reactive silica, okay, also standards, okay, they put limitation for the use of this fly ash. When it comes to natural pozzolan, the same amorphous phases, harmful clay, because they are very heterogeneous, they are coming from quarry, natural somehow deposit. Very often you have harmful materials, especially like clay. So very often those materials, they have high water demand, okay? And of course, the reactive silica to assure certain reactivity. And when it comes to limestone, for example, the percentage of calcium carbonate, you will see in standards, okay? In Sri Lanka, for example, we need to achieve exactly what EN 197 is more than 75%, okay? Of calcium carbonate. You have clay content, okay, through methylene blue test, and you have the total organic organic carbon. That is also a very important parameter. You will see, for example, in the EN standard, you have the low grade, what is the L, and the high grade, the LL, okay? And that is what we have in Sri Lanka, is a high grade in, for example, just an example, our sandstone. Therefore, you see there are quality indicators. And this product has been used for decades. Indeed, if I look the legacy horsing, okay, this is the legacy, our legacy. In 2000, let's say 14, okay, we have used total, okay, in our portfolio all around the world, okay, out of 140 million ton, we have used about 40 million ton of these mineral components. Okay, therefore, technology are proven, they are in standard, and this is what we are going to discuss about it. Now, chemically, when I look to those products and I put them in a ternary system that is calcium silicate for the basicity and aluminate, okay? You see here what you have. You have latent hydraulic product, OPC, okay, with a basicity very always above 2, blast furnace slag, I mean a good one will be over 1, and C-flash, these are from bituminous or lignite coal that is really mainly in the States, we find them in States and very little in Germany. Okay, they have also a certain basicity above 0.5, okay? Therefore, these are what you call, these are the latent hydraulic, this is really the hydraulic one, and you have the aluminosilicate one. These aluminosilicate, they are not reactive, like for example, silica fuel, okay, a very noble mineral components, okay, but silica fuel alone is inert. Is any of this material, they are inert. Therefore, you need to activate them. Okay, therefore, the activation comes through calcium because they have the silicium. Okay, this is why when we look, for example, calcium silica ratio, okay, from pozzolanic material where basicity is below 0.5 to latent hydraulic between 0.5 to 1.5, and above 1.5 we come to hydraulic like clinker. And very often I say clinker is above 2. And this is what it comes to when it comes to hydration. Okay, I have been presented this to some of you, but for those who have not seen it, this is, when I talk to hydration reaction, from OPC we can see the silicate phases. In presence of water, you form what we said, the calcium silicate hydrate. Okay, the CSH. Very small fibers, okay, in the microstructure where the length is below 50 nanometers, as I said. And you have portlandite. Okay, these are big crystal. Okay, now, strength is coming from calcium silicate hydrates, and very often when you have difficulty in terms of durability, because these are soluble. These are soluble, okay? Even though they are important to keep a certain basicity for concrete, a certain pH to protect reinforcement, but too much of this product will also create other big problem in terms of durability. This is why when we combine them in a composite cement design, we have another reaction called the pozzolanic reaction, not the hydration reaction, that will complete this, turn the excess of calcium hydroxide to calcium silicate hydrate. And very often this will come after, let's say, 28 days and after 28 days in general. This is why when we are testing our OPC and we test our composite cement, if you test after 58 days or at 91 days, you see that most, if not all, of the composite cement outperform OPC product, just because we continue to develop calcium silicate hydrate with time. Okay, therefore, by eliminating the, not totally, but eliminating a big part of the calcium hydroxide, we have here reducing the possibility to have big pores. Okay, therefore we are more having gel pores. Okay, and this makes your concrete more dense, therefore more durable. And when we come, for example, to leachability, when it comes to any problem that happen, when I see, for example, calcium hydroxide from OPC for different percentage of flash or slag, you see the amount of calcium hydroxide will drop drastically. We will always have enough to keep a certain basicity pH in your concrete to protect your reinforcement, definitely. Okay, there is no worry about this. Okay, but what is more important, that the dissolution, or I would say the leachability, will have high chemical resistance. Okay, is just because we are eliminating a soluble salt, yeah, a kind of soluble salt that is Portland hydride. come now to the last part of the presentation about international standards. I will discuss here about the two big standards that most of the national standards all around the world get inspired by these two standards. Now, this most widely in the US, as I said, there is three separate standards that may apply depending on the category of cement. We have for OPC is what we call ISTM C150. Okay, the blended hydraulic cement, this is a C595, and also one standard with a big interest from the industry that was developed. It's a performance-based specification standards. Okay, a performance-based specification standards. That is the 1157. Okay, the ISM 1157. Okay, that are the three standards that coexist in the ISM. Now, in Europe, the 31 European countries, they operate under the EN 197/1. Okay, that is the 31 European countries, they operate all under these standards. In my presentation, I will talk about the BSEN 197, the UK, because in Sri Lanka, okay, this is our reference standard. That is composition, specification, conformity criteria for common cement. And even though I will, because very often when we talk about this standard, I can just take a couple of seconds to mention that very often they are amended. They are continuously amended. And very often we are using sometime, for example, the 595 or the 197 that are superseded by another one. Therefore, what I'm presenting today is the state of amendment. Therefore, the 197, okay, was amended this year. Okay, the 595 was amended this year. Therefore, the new amendment. Therefore, what I'm going to give you today is today's situation with all these standards. Okay, because that is very important, because very often we get somehow we are misled by standards that are not updated. Okay, now what is ISTM? Because I know I'm graduated from Canada. I'm very much used to ISTM standards, but it was good that I just give you some some historical. It's originally known as American Society for Testing and Materials. This is why we call it ISTM. And it began in 1898 when engineers and scientists gathered to address frequent rail breaks, okay, in the booming railroad industry. Therefore, today, known as ISTM International. Therefore, when you will refer to ISTM standard, it's international, and which is one of the largest voluntary standard development in the organization in the world today. And as I said, there are three coexisting standards, the 150, the 595, and the 1157. Okay? Now, for the ISTM, the C150, that is standard specification for Portland cement. Okay? Originally, it was approved in 1940. This is just before the Second World War that ended in 1945. Okay? And this standard prescribed ingredient and proportion, but with some, you see I put in there with some performance requirement, because originally it was a purely prescriptive standards. Okay? And last year's performance-based requirements were introduced. Therefore, it was updated. Okay, this standard was updated. And this standard covered 10 types of Portland cement. Okay, type 1, that is used for special, is when special properties specified by another type are not required. I would say when I take the type 1 is like our SLS 107, part of it. Because here we have the strengths class, okay, in Europe that we don't have in the ISM, but the SLS 107 can be compared to the type 1 ISM 150. But you have also the type 2, that is for general use for moderate sulfate resistance. This is a type 2. But in the type 2, you have a subcategory called type 2 MA. This is when you can be moderate sulfate, but at the same time, moderate heat of hydration. Okay? Now, you see, type 1 is your OPC general use. Type 2 will be your moderate heat and moderate sulfate. Type 3 is for your high early strengths. That will be, for example, if I come to the EN, okay, if I compare a 32.5 OPC and a 52.5 OPC, that we don't have in our Sri Lankan standard, the 52.5. That could be somehow, we can compare them like that. After, you have a type 4, and that is really low heat of hydration. And I would say today, almost, I personally do not know, okay, such a kind of product that is in the market, that is sold according to the type 4, okay? And you have the type 5, that is for high sulfate resistance. Now, you see, mainly there are 5 types, but also you have a special, somehow, a category with moderate heat, and the A is when we have air entrainment, okay? For example, for frost resistance, we need to entrain a certain amount of air, okay? And some value proposition, okay, in the ISM from the cement producer, you develop a finished product. When you produce your concrete, you develop the air needed, okay? This is prescriptively, okay? Therefore, they can do it in that way. If you come to the EN letter, you see we don't have this possibility. Therefore, these are mainly 5 products, I would say mainly 5 products. Type 1 ISM is really for general use, OPC. Type 2 is moderate and sulfate and moderate heat. Okay, that we do not have somehow in the EN. And the type 3 is for high early strength OPC. Type 4 is for low heat of hydration, and type 5 for high sulfate resistance. And these are all OPC based. Now, when it comes to the prescribed chemical composition here again you see that requirements, okay? First, it is said in the note 2, it is said that it is important that before you specify them in your market, assure that those products are available. They don't prescribe a type 4 when nobody produces it in your market. That is important. After that, the chemical, that is prescriptively chemically done. Okay, you have aluminum content maximum 6%. And now you know when we talk about moderate sulfate and moderate heat, okay, why we have for the type 2 the requirement on aluminum content. Okay, now Fa2O3 iron, you have also 6% maximum, and the BC is said here clearly that does not apply when sulfate resistance limit or when heat of hydration limit are specified. And this is the performance base, I will come later to it. Okay, therefore you do not have to fulfill this requirement if you make a performance based test. Okay, now magnesium oxide, okay, therefore you have limitation 6%, it will be 5 for European for SLSI. This is for magnesium oxide. After you have SO3, depending if you have less than 8% or more than 8%. You see, when more than 8% here, you cannot apply it for moderate sulfate and moderate heat, because this is a product that develops heat, and problem with sulfate is from the C3. But when it's less than 8%, okay, you have to use average 3% on SO3, 3.5 when it is for type 3, and 2.3 for type 4 and type 5. Okay, here again, there is a performance-based test saying that if you perform a test on heat or on sulfate and you pass the performance test, you can be above 8%. Okay, that is really a big move that those standard has made the last decades. Now, LOI, okay, 3%, nothing really soluble, insoluble residue, 0.75, okay, we are around 1. After C3S, C2S, here you have also limitations, especially for heat, for low heat cement. Okay, this is why you need to develop what you call a balytic cement, and nobody will do it today. These are cement where you have more C2S than C3S, and these are very lazy cement at early age. In some country, you will find them because from the raw material, okay, very often they have a high amount of C2S. They are not as low as 35% in C2S. For example, here, normal C2S will be around above 55, 60%, and they will be below 55. Okay, that is for C2S, C3S. After, you have also another very important that a lot of people don't put is the sum of C3S and C3A. You see, when I show you the heat of hydration, the most two clinker constituent that contribute to heat is 3-calcium aluminate, C3A, and 3-calcium sulfate, C3S. Therefore, C3A and C, you have to fulfill the requirement, okay, that it should be below a certain number, okay. Now, when it comes to sulfate resistance here, again you have limitation in terms of maximum for the C4F and for the C3A, or when you have no C3A, there is another aluminate ferrite, calcium aluminate ferrite that is 4, okay, and you should be below 25%. Okay, not to be only low in C3A, let's say 5%, but you need to have also less than 25% when it is prescriptively, fulfilled. But when you go performance-based, there are other tests as mentioned in the B here on table 4, that is more tests on sulfate test. Okay, therefore, that is chemically. And when you come to optional chemical, okay, for moderate sulfate resistance, 8% for the type 3, okay? Sulfate resistance, 5%. Because these are the requirement. If you come here, the requirement for when it comes to C3A, 8% and 5%, what you see, 5% here, okay? And the C3A for the moderate, where I can find here, the C3A maximum 8% here, you see? 8% for moderate, and 5% for high sulfate. This is what you can see here. Okay, that is optional. Therefore, I can produce, for example, high early strength cement. Okay, and I demonstrate that my C3A is below 8% or my C3A is below 5%. In this case, okay, I can declare it as moderate or high sulfate resistance. And for alkali, okay, you have a test here on equivalent alkali for low alkali cement. Okay, but it's clearly specified here that this is not mandatory if it is not used for when you don't have reactive aggregate. It's only when the aggregate is reactive. When it's not reactive, you can go above 0.6. Okay, because the main problem with alkali, you can go at 0.7, 0.8. Okay, only the problem is when you have a reactive aggregate, okay, you have to stay below 0.8. This is from the OPC based. And from the physical requirement, okay, you have air content, especially for air and train, 22% maximum, okay, and minimum 16%. Okay, that is really the requirement, 22% and 16% when you entrain air. And when you do not entrain air, it's 12% maximum. And when you know the ratio, if you measure the air content in your motor, it is about 5 times what you get normally, average value, to what you get in concrete. Okay? Therefore, after that, you have the fineness, specific surface, okay, with air permeability test. You have limitation here, but the limitation you see is quite coarse for the minimum. And here you have requirement 430, okay? And it say that this maximum limit do not apply if, you know, the limitation on C3S and C4A, C3A, if it is equal or less than 90%. Therefore, this requirement will not apply when it is moderate heat and moderate sulfate, okay? Because we know that these are the three constituents of clinker that can cause a problem. After we have autoclaved, okay, for freeline, for NGO, you know, you have also a performance-based test at 0.8%, okay? Therefore, you should not exceed this value. Now, in terms of strengths, I will show you one slide when we compare ISTM to EN, because this is, again, it is very difficult to compare them, okay? I will explain you why. But if I look, generally speaking, when I look to this table in terms of compressive strengths, okay, the maximum strengths, what they will get, that the minimum requirement is a 32.5. But as I said, they don't mention 42, 52 as we have in the EN standard. But according to ISTM, the minimum requirement will be 32.5. Okay, and they test at 3 days and not at 2 days. Only 1 day is for type 3, and this is for high early strength cement. Again, for setting time, here they have requirement 45 minute minimum. Okay, and they don't specify final setting, only initial setting with minimum and not longer than 375 minutes. Okay, therefore minimum, maximum. These are the two requirements. Now, these are the optional physical requirement, the table 4, that is the performance base. Therefore, what it said that, for example, if you do a 4-set test, okay, if your final penetration is 50%, okay, SO3, you can increase the amount, no problem. Okay, for the heat of hydration here, therefore C3A, you can exceed the limit if you can assure that for your moderate heat and moderate sulfate here, you have 290 for the heat, okay, at 7 days, and when it is for low heat cement, okay, is 250 and 290 at 28 days. This is a performance base. It's not prescriptive, it's really performance based, because you do the test and you look after your performance. Okay? Now, in terms of compressive strengths, again, there is limit, but are very, very close to what is physically required. Now, in terms of sulfate, you see they have a sulfate resistant test at 14 days, okay, and they will tell you here required only for the type 5. Type 5 is the high sulfate resistance OPC based. And for the other type, okay, here it's mentioned that cement meeting the high sulfate resistance limit of type 5 is deemed to meet moderate sulfate resistance requirement of type 2 and type 2 moderate heat. Therefore, you have to fulfill this. And they have also a brain test on the turbidimeter test, okay, where they will give some limitation, because this is what I said always to my colleague when we talk about brain. Okay, normally air permeability brain test is for OPC, is for really OPC, but when you come very often to compare them with some particle size distribution, it is much better to measure particle size distribution than brain. Okay, that is important that I can mention that here also. Therefore, that is about the C150, and as you could see, the C510 is really OPC, 5 main type product. Okay, general use, moderate heat, moderate sulfate, high early strength, low heat, and high sulfate resistance. That is OPC based. Now, here is just before I go to the C495. I have 2 other slides. One is saying that difference in standard mortar testing is like the red apple and the green apple. They are apple, but they are different. That is important to know because they do not test in the same way. In the, you know very well the EN is fixed water cement ratio, graded sand up to 2 millimeter. We use shock table, we use vibrated table, and you have prism. In the ICM, it's different. For OPC, it's fixed. Water cementage 0.485. For blended cement, is variable because you achieve a certain flow test. Is not fixed water cement ratio. After that, for the sand, they have a monograin sand called sand of Ottawa, very fine sand. Okay, they use tamper manually to compact, and they use cube. Therefore, when we compare, and this is done by our legacy horsing, okay, at our R&D center, where we have, as we were in all this market, ICM market, okay, we have tested same cement in both standard, and you see the 3 days ICM is relatively equal to 95% of the 2 days. The 3 days is 95% of the 2 days. This is why I say is relatively low in strength. And for the 28 days, the 28 days for ICM is equivalent to 75% of the 28 days. Okay? That is somehow what you can, if you have to compare them, this is a kind of like a trend that we can have. And another one is the calculation of the main phases of the clinker. Okay, with or without limestone is not the same. Without limestone, you have to assure if you are in the condition where most of the time, okay, the aluminum to iron ratio is above 0.64, yeah, even above 1. Okay, you have a way to calculate it. But if it is below 1, below 0.64, you do not form C3A. Therefore, you have another way of calculating. This is very important because very often, okay, some cement, and you will see now in the EN, the C3A is 0. Therefore, they need to calculate it in a different way than this way. And also, when you use limestone, very often a cement producer produce OPC without limestone, and they will produce OPC with limestone, and they will always report the BOG calculation, do not considering the limestone. Therefore, you need to consider the limestone. Therefore, you take your reference clinker OPC value without limestone, okay, and you correct it, okay, by subtracting the mass percent of limestone and the mass percent of, if you use inorganic mineral, let's say, processing addition. You have to do the correction. This is a very important part because very often we are talking about C3S, okay, and we do not take this into consideration. Now, that is the OPC based ICM. Now, when you come to the 595, that is blended hydraulic cement, okay? It was approved in 1967, and this standard the same the last, let's say, years. Some performance requirement has been added, okay? Therefore, the 595 that I knew 20 years back is not the same that the 955 we have today, okay? And it covers 7 types of blended hydraulic cement. In terms of terminology, you see they call blended hydraulic cement, okay? For both general and special application. Now, we have 3 types. They are binary hydraulics. When I say binary here, is mean clinker plus 1 mineral components. This is binary. You have clinker plus 1 because both are hydraulic. Therefore, they are binary hydraulic blend cement. You have the type 1S. This is slag based. That's what you call Portland blast furnace slag, in which the slag content can go up to 95%. This is somehow equivalent to our SLS 1247. Up to, we can go up to 35%. This is our SN2BS, 35%. But also, in the type IS, if the slag content is more than 70%, it is permitted to add hydrated lime. Yeah, that is, I told you, this can be an activator when you are above 70%. Okay, you can add this hydrated. Therefore, you will see, if you see type 1S like this, this means is type 1 with slag, and 80 means 80% slag. And in this case, they can add hydrated lime. Okay, when it is type IS, for example, type 1S50 will be 50% slag. There you don't have hydrated lime. Now you have the type IP. Type IP is a Portland pozzolan, okay, in which the pozzolan content, okay, the pozzolan content can go up to, 45%, okay. Therefore, this is like our SLS 1247 up to 35%. Okay, you go one pozzolan and clinker up to 40%. Therefore, that is like our SLS. Now, you have the type IL, type 1L. Type 1 is a Portland limestone cement, in which here the limestone maximum is 15%. More than 5, up to 15%. Okay, and this is called blended hydraulic cement. In our case, we call it Portland limestone cement. Okay, example is our SLS 1253, where we go up to 20%. This is because it's like on the E and the same to A, LL in our case. Okay, therefore we see there is a good similarity. Okay, not the same proportion, but we can have some comparison on the product type. I'm talking about the product type. Now, you have 4 types. These are now ternary. Ternary means you can put more than 1 mineral component. You can put 2. And in the EN, that will be composite cement. Portland composite cement. The same to A and same to BN. These are multiple blend. We'll discuss about it. What is interesting here, you see you can have 2 pozzolanic material, maximum 40%. Not 1, you can add 2. Okay, and this will be the type 1T for ternary. After you have the type 1T SP, where you can put 2 mineral components, in this case slag and pozzolan. Maximum will be 70%, but you cannot add more than 40% of pozzolan. You see, in all these 595, maximum in pozzolan is 40%, limestone 15%. Slag you can go up to 95%. But in the ternary system, when we talk about the type 1T SP, maximum will be 70%. Okay? Now, you have the type 1T, this is now pozzolan and limestone. Okay? Ternary blend, when maximum pozzolan will be 50% and limestone 15%. Therefore, here we cannot go to 70% because there is limitation. Pozzolan 40%, limestone 15%. Okay? Therefore, that we will call, for example, type 1T, P more than L. Okay? If you see this, this means you have pozzolan and limestone, but the proportion of pozzolan in this ternary system is higher than the limestone. And you have the type 1T, this is now slag and limestone. Okay? Where you can go more than 70% in slag, and in this case, again, you can add hydrated lime and 15% limestone. Or if you are below 70% of slag, you can add maximum 15% of limestone. Okay, you see, these are the 595 blended hydraulic cement. I call it 7 types. Okay, but indeed you can say 9 types because you have one additional one here and one additional here. But there are 7 types. Okay, therefore the 150 is 10. Here we have 7. And if I now to the 595, if you look the special property for sulfate and low heat, because the 7 type of blended cement, as I said, here blended hydraulic, these are for a common cement. Now, you have for sulfate resistance, okay, where attributable to special characteristic of slag, pozzolan, and limestone. Therefore, you can have, for example, a type 1P okay, that is moderate heat. For example, 1P here, that is moderate heat. Therefore, you have to add MH, okay, for moderate heat. And this is equivalent, for example, to the type 2 moderate heat in ISM 150. This is the version OPC based, and this is the version blended cement with the same attribute. Okay, same for low heat, same for moderate sulfate resistance, same for high sulfate resistance, and for air entraining. Therefore, you see in the 595 is like your 510, the clinker base, but it is the version of blended hydraulic cement. Okay, you have blended hydraulic cement with exactly the same attribute. Okay, in terms of low moderate heat, low heat, moderate sulfate, low sulfate, and air entrainer. Okay. Now, important what I said here, similar special property as ICM. Therefore, what you achieve with OPC, you achieve it also with blended hydraulic cement, according to the 595. Now you have here the prescribed chemical composition. Now you see it shrink very much. Therefore, we have MgO, okay, limitation only for pozzolanic material, for the type IP, okay, and IT, and here the type ternary is when the pozzolan you see here is higher than slag or limestone, maximum 6%. After you have the sulfate reported as SO3, 3443, but you see there is a B here, and the BC is, for example, it is permissible to exceed the value if we demonstrate that according to the test method here, the 1033, okay, there is no increase, the increase of SC3 will not develop expansion. Above here, 200 micro deformation, 200 micrometer per meter after 14 days. This is a pure performance-based test. Pure performance is very innovative. Therefore, do whatever you want. If you fulfill the performance requirement, you are qualified. Sulfate, this is mainly for slag base, 2%. After you have insoluble residue, you see here they go up to 1, not 0.75, up to 1. This is according to our SLSI. And LOI here, 3, 4, 5, and 10. But with the D here, you see for the D here, they said that for ternary blend cement with limestone, you can go up to 10%. Okay? Therefore, you see, it's very, very pragmatic, very simple way, give you the most important parameter to consider when we talk about application. And very simple for engineers like us. I mean, like me, I understand very much like this way. Okay, when I look to a product, then when you have 1,000 chemical stuff that I don't know how to interlink one to other, and having no glue on the performance side, because it's not a way base, but it's a purpose base. You agree with me? I don't need to build a bridge. The purpose is to build a bridge that lasts more than 50 years. That's performance based. Now, the limitation on the limestone, okay, is exactly like what we have, similar, same indicators like in the EN. For example, calcium carbonate here is 70%, in the EN is 75%, like SLSI, same, 75%. Methylene blue, 1.2, and total organic carbon, maximum 0.5. But in the EN and in our SLSI, we have one here is the 0.2. That is the high-grade calcium carbonate, the high-grade limestone. Therefore, they don't have 2 grades, they have only the L. We have L and LL in our Sri Lankan standard and in the BSEN 197. Okay? Therefore, that is also important for people who are not used to somehow to work with limestone cement, okay? Because those products have the intrinsic quality control requirements. Now, requirement for pozzolan now to be used, well, I have to use a pozzolan or a slag, okay, to blend the cement or to ternary system slag base when the slag is below 25%. You see there is requirement on the fineness for the limestone, for the pozzolan. For example, the maximum in wet sieve on the 45 micron cannot be more than 20%. If it is too coarse, okay, you cannot take it. Activity index, okay, 75%. I will explain what is activity index. 75%. Performance based. LOI on the pozzolan, if it is natural pozzolan, is 10%. Fly ash 6%. We are around 5. What we accept, okay. Silica fume 6. Therefore, activity index is, we have our reference mix with OPC and we substitute OPC with, in the case of pozzolan, 35%, and in the case of slag, 70%. Clinker factor here, 35% less, here 70% less. And our activity index here at 28 days should be 75% of the reference. I should achieve 75%. Okay. If you test the 56 days and the 90 days, you are above 100%. Now, the 595, you have now the physical requirements on fineness and density. You have just to report it. There is no limitation. You need to report it. Now, on autoclave expansion, okay, there is a maximum value here, 0.8 and 0.2 for all category here. And the B says the specimen shall remain firm. Therefore, you have to assure that you don't have any expansion due to autoclave like magnesium or free line. Okay. Now, when it comes to time of initial setting, okay, they put not less than in minute and not more than in hour. Therefore, you should be between 45 minutes and 7 hours. I mean, not difficult to achieve here. Air content, in case that will be 12% for non-air, of course. And compressive strengths, here again, it's, I would say when I look here, 13, 90%, about, let's say, a little bit more than 10, 32.5 R or 42.5. 25, this will be our 32.5. Okay? But what I said, the limit, the minimum limit, according to ISM, is a 32.5. You can go above, no problem. But there is no category for such a kind of like 42, 52. But you should achieve the minimum of 32 that is requested for the market. Above is not really, a boundary to respect. Now, the 595, now these are the physical requirement, air content, compressive strength. Now you see heat of hydration. That is important, the heat. Okay. The heat is said that you have for moderate heat and low heat requirement at 3 days and at 7 days requirement. You have some requirement to fulfill. For compressive strength, nothing special. For air content, nothing special. Of course, 12% when you don't have air, and when you have air, 1622. Okay? Now, you have requirement for water requirement. This is according for the compressive strength. As I said, in this test is not fixed water cement ratio. You have to fulfill a flow of 100 to 115%, okay, of the reference mix. Therefore, you should not have more than water cement ratio above 64 when you are talking about low heat, and there is no requirement here. When it is for low heat, you should not have a water requirement above this value. Therefore, maximum water cement ratio is 64 to test, and you should achieve at 28 days minimum 21 megapascal. Minimum 21 megapascal. Therefore, you have also sulfate resistance. That is very interesting because this will give you expansion limit. Okay, at, let's say here we for moderate sulfate resistance is at 6 months. High sulfate resistance 6 months here is 1000 micro deformation. Here is 500 micro deformation. But there is a limit at 1 year for the high sulfate resistance should not exceed the 1000 micro deformation. Therefore, you see, if you already got for the moderate sulfate resistance 0.5, it means you are close to be high sulfate resistance. Therefore, straightforward and very very pragmatic. That is really the 595. 595 is similar to the 150 in terms of OPC. Okay, same attribute for sulfate resistance, for low heat, for same attribute, but it is a version of blended cement. They have performance based like OPC, where prescription are not only on the chemical. Okay, that is also important to note. Now, the last one is the ISM 1157. This is standard performance based. This is only a 4-page standard, only 4 page. Just remember me the Australian standard cement, the most simple one, okay, to understand for engineers and to fulfill. Really, very simple one, straightforward, very performance based. This is originally approved in 1992, the standards, 1992, and there is, you see, no restriction in terms of composition, no restriction in terms of composition and constituent. They classify cement based on specific requirements, okay, related to concrete performance. Therefore, for general use application, for high early strengths, for resistance attack to sulfate, and for low heat. This is exactly the same what we saw in 150 and 595. Okay, there is no really, and then you have optional requirement are approved for the property of low reactive alkali silica, because on the 595 there were a limitation for alkali silica reaction in terms of alkali content, and they took it out. It is on the 1157, and it is said that in this case this is optional only for the 595. Here in this case is optional for alkali silica reaction, okay, and for air entrainment. Therefore, if you want to have A or not A, it covers 6 types. And therefore, as I say, is equivalent really to the 150 and the 595, but with no restriction in terms of composition. General use, high early strengths, moderate sulfate, high sulfate, moderate heat, and low heat. And you have option R that was in the previous the 595 blended cement, the version 2000. The 2014 it was there, and now the 2020 is not anymore there. The 2020 was approved April, beginning of this month. It was approved, and they took it out. Okay, and you have, it's an option for the 1157 for alkali silica reaction on the 0.6 for low equivalent alkali, and option A for air entrainment. Therefore, here the chemical composition not specified. However, the cement shall be analyzed for informational purpose. Therefore, important mention note here that concrete performance, it is said in the standard, depend on many factors like characteristic of other concrete materials. Yes, like aggregate, for example, like superplasticizer, like the water, okay? The mix design, at which water cement ratio. Therefore, very often don't over-design your cement content. Don't over-design it, okay? Production, handling, the environmental condition, okay? In which condition my concrete is going to be used. That is important to understand. Therefore, performance property in concrete, including permeability, resistance for frost in Nordic country, okay? Additional info may be obtained through the use of comparative testing concrete. And you see our motivation in Sri Lanka, our motivation, okay, to develop these collaboration spaces. And those collaboration spaces will somehow provide state-of-the-art performance-based tests on concrete, not on cement, okay, to assure service life modeling fulfillment, okay? Now, the physical requirements, fineness has to be, okay, of course, has to be somehow measured. Autoclave length, okay, maximum 0.8, not less than and not more for setting time 45 minutes and 420 minutes. These are the boundary for setting time. Air content normal 12%. Compressive strength, you see, maximum you can read at 28 days is a 32.5, average 32.5 according to the, okay, and at 1 day is only for the HE requirement, is about 10 MPa. This, as I said, 32.5 R at 2 days, okay? Therefore, you have the 3 days, 7 days, and 28 days. And the 28 days, even though not required for high early strengths, for moderate sulfate resistance, and for moderate heat. Not required. The heat of hydration, only for moderate heat and low heat. After you have motor bar expansion at 14 days, and you should not exceed 200 micro deformation. And also they have the sulfate expansion. This motor bar, by the way, this motor bar is not autoclave. The motor bar is a test to see if your internal sulfate, you have internal sulfatic attack. Because when you have a sulfate problem, it can be internal or external. When we talk about sulfate resistance here, what you see, according to the 1012, this is external. But according to the 1038 is internal. Because this performance, they tell you, whatever you want to put on SO3, optimize your compressive strength. But they should not exceed the 200 micro deformation after 14 days. Very performance based. Okay. That is all about the 1157 for the physical requirement. And the optional one is on air. Normal. Now you know 22 for when it is entrained and non-entrained, 60. Okay. For R, this is for alkali silica reaction. Okay. You should not exceed at 14 days or 56 days a certain expansion. The same for all from GU to low heat, all of them. Okay. 200 to 600 micro deformation. Now they do stiffening test. Okay. Is a penetration test. 50 maximum. Okay. A minimum 30. And compressive strengths, you have only the 22 MPa for moderate heat and 22 for moderate sulfate and 22 for moderate heat. And you see they have one test that is a drying shrinkage. That normally the drying shrinkage is made on concrete according to the 1157. It was on the 595 in the previous standards. That is a blended cement. It is removed now in the 2020 version. But you find it in the 11.7. But this is the motor test where you should not exceed, and this is only when it is requested by the purchaser. Now, I finish here with the ISTM. Now we come to the BSE 197. Okay, it is originally initiated in 1969 by the European Economic Commission, and the first draft at the early 80s was given to the Comité Européen de Normalisation. This is in French. This is Technical Committee 51. Now, defines 34 type of cement in total. When you look the ISTM, if I take the integrated 3 coexisting ISTM, we have about 23. Okay, of which you have 27 distinct common cement grouped in 5 main type of cement. You have the SEM1, SEM2 for Portland composite. Portland composite is the SEM2. It's not blended, it's composite. After SEM3 is blast furnace, SEM4 pozzolanic cement, and SEM5 a composite cement. You see, it's not Portland composite, but it is a composite cement. You will see in terms of composition. These are the 27 distinct common cement, but also they have 7 sulfate resisting common cement grouped into 3 main cement types. You have sulfate resistant OPC based. And this sulfate is OPC based, you have 3 categories of C3A. 0 at the 3% or 5%. Okay, in Sri Lanka, we have this value here. C3A, the ISM, The ICM, if I go to ICM, the 150, the OPC, below 5%. They don't have this too. They don't have the sulfate resisting cement with 3% or with 0% of C3A. But in the EN, they have three type of type 3, ICM 150. They have three type. The 0%, 3%, and 5% C3. After you have the sulfate resistant blast furnace cement now. This is the same 3B and the same 3C. Okay? SR means sulfate resistance. There are no requirement for C3A. This is thanks to the blast furnace slag. Okay? Now, you have also sulfate resistant pozzolanic cement. This is the same for ASR. That is what we have in Sri Lanka. I will show it on the table, next tables. And the same for BSR. This is pozzolanic where the somehow the so AB is just substitute. You can go higher in pozzolan content here, and here again you see there are requirements for C3A below 9%. The requirement is not there for slag cement. This is why whenever you talk high sulfate resistant cement, most of the international projects are slag based. Okay, are slag based. That is one of the. There is, you don't have restriction on the clinker. More flexibility and more performance based and proven, really proven. Now, they do not include here. They do not include the low heat special cement covered by EN 14216. I'm very interested with the topic of low heat because Sri Lanka is a country where most of our concrete are poor at temperature 30 degrees and plus. Okay, and if you talk to our ready-mix industry players, okay, this is where they have the maximum of challenges is this heat. Okay, now composition and notation. Okay, here you see the 27 product, what we call common product. The type 1, this is Portland cement. The type 2, you have Portland slag with two categories, the A and the B. A, you can go up to 20%, and the B, you can go up to 35%. After you have the silica fume cement, AD, maximum 10%. After you have the Portland limestone, where you have natural pozzolan or somehow the Q here is burn oil shale, calcine, natural calcine. And you can have also two classes here, A or B, up to 20%, up to 35%. After you have the Portland limestone, Portland fly ash cement, again here you have the same to AV, same to PV. The W here is for calcareous, this is like fly ash type C, okay? Here again the same 20 for the A class and 35 for the B class. After you have the Portland burn shale cement, this you have the cement here in Switzerland, burn or shale, okay? Here again you can go to 20 or 35% for class A or B. You have the Portland limestone cement. Here they have two categories. You see you have the L category and the LL. This is low grade, high grade. Again, A and B, 20 up to 20, B up to 35. After you have the Portland composite cement here. Portland composite cement where you have a multiple blend. You cannot go, you don't go only with one blend, okay? It's like the 1T according to the ISM 595. Composite is a multiple blend where you can mix any kind of mineral components up to from 12 to 20% for the A class and from 21 to 35% for the class B. After you have the same three blast furnace slag, these are slag based. From 36, you can go for the C up to 95. This is exactly like you have in the 595, the type 1S up to 95%, according to ICM. But here they have three categories. Okay, here they have three categories. There is up to you. They give you the flexibility because you have to fulfill performance tests, compressive strength, heat, and so on. Okay. Therefore, the performance test will put you the boundary. Therefore, they give you the whole flexibility, but the boundary are there. Okay. Now, it's more innovative for me, I feel it. Therefore, the FEM4 pozzolanic cement, here again, you can mix 5 different pozzolanic material, okay, excluding blast furnace slag because this is latent, and excluding burn oil shale, and of course, the limestone. Therefore, these are the, why we call them pozzolanic. These are purely pozzolanic, huh? That are the type SEM1, SEM2, SEM3, SEM4, SEM5, and the 27 class. After you have the 7 type of sulfate resistant. And this sulfate resistant common cement, you know, you have, as I say, SEM1 with 3 class of C3A, SEM3 based on slag from 20% clinker factor down to 19, and this you can go from 66 to 95% slag. And the SEM4, these are pozzolanic material, SEM4A and SEM4B. Okay, these are all sulfate resistant. Now, we know that our Sri Lankan standard, we have OPC, we have blended hydraulic, and we have Portland limestone cement. Now, when I look to the EN, because we are inspired from this standard, we have the type 1 here, fulfill exactly the same one here. We have the 1247, therefore we have part of the SEM2 cement here, not all of them. We don't have Portland composite, okay? We don't have the Portland fly ash cement, the Portland silica fume cement, we don't, but we have in the 1257, 1253, we have the SEM2ALL, huh? We have this, I call it, limestone, high-grade limestone. This is, for example, Sansa, okay? And when it comes to sulfate resisting type, we have our SEM4A SR, okay? That is our sulfate resistant cement. And of course, for the Portland cement here, for this SLSI 1253, that is our Portland limestone cement. But according to the EN, okay, this cement is part of the SEM2, or they are SEM2 cement. And you see, we produce according to the LL in Sri Lanka. Our Sri Lankan standard do not have the B, therefore up to 35%, and we don't have the L class. We have only the LL. Okay. Now, this is from the composition. Therefore, just to see where we stand compared to the European, okay, we still miss Portland composite, we still miss slag cement, some of the pozzolanic, and also some of the SEM5. We miss them. Now, when it comes to mechanical and physical requirement given as characteristic value, okay? Now, we know very well in Sri Lanka 32.5 and 42.5. We know the N class and the R class because this is our standard, Sri Lankan standard. If I take the 107, the 1247, and the 1253, okay, they are within this range of compressive strength class. They have added the European standard for only for SEM3 cement in slag cement, high slag cement, the L, 32.5 L, okay? This is normal, this is rapid, this is low, you see, and the requirement at 7 days is 12 MPa, and not 16 MPa, it's 12, okay, for the 32.5. And when it comes now for the 42.5, the requirement is exactly like the 32.5 is 16 MPa, okay? Now, and more requirement for the 52.5. Okay, now, when we look now to the other classes, the 52.5, we do not have the 52.5 in Sri Lanka, even though if I take the 42.5 R here, that is 20 MPa, it can be equivalent to the 52.5, and at the same time, the 42.5 R, that is between 42.5 and 52.5. If you look at our product, we are around 55 MPa, and you are also a 42.5 N. Therefore, but this is not that. Is equivalent to 52.5 cent. Therefore, we do not have that. We have the soundness autoclave. We have this test. Okay. And when it comes to low heat, according to what there is requirement for low heat when it comes to low heat cement, because I have presented because low heat common cement are noted as LH. They have this LA, they have this low heat. Therefore, we in Sri Lanka, for example, we are obliged to send our cement to get the EN19, as you can read it here, EN1971. Now it will be a version 2020 because this is the last one. You see, it's the same to 4A, 42.5 and you see, is sulfate resistance is fine. We have it in Sri Lanka, but the low heat is not in our standard. Yes, it will cost us millions of rupees just to send it out of the country to get this certificate. And we are talking about a product that fulfills the standards. Okay, that is just a small, I would say, for me, a lot of innovation can be done. Okay, if we can tackle this in a more, let's say, objective and not subjective way. Okay, now from the chemical requirements given as characteristic values here, you have LOI, insoluble residue, sulfate content, chloride content, and the pulsonicity. Okay, therefore here when I compare to our SLSI here, okay, I did not put the number because you have SEM1 and SEM2 and SEM4. Therefore we have our the OPC and the blended cement. And for the chloride is for all product below 0.1. Even though it is mentioned if it is going for pre-stress, a value below 0.1 can be requested by the purchaser. Okay, that is really the boundary condition. What do they have? Now, when it comes now to the properties for resisting sulfate resisting common cement, in terms of sulfate here, they have the, as I said, 3C3A and the SR on C3A, and the calculation, they still do not have a method for calculation. They are working on the method, but ASTM, they have their method, okay, to calculate it. But according to EN, they are still working on it. And also you have here the requirements, okay? Therefore, when it comes to our SLSI, you see we have the 1247 because we do not cover all the EN197, therefore this is where we stand. Now, with this one, just before ending, there is also a table in the showing list of common cement considered as sulfate resistant by national standards, by national standard. But they do not, I would say, but not included in table 2N or not fulfilling the requirement in table 5. But they are considered as national. At the national level, they are, because you have national amendment as sulfate resistant cement. I just focus on, for example, for UK, the SEM2BV, it is a sulfate resistant cement, or a SEM2AV and SEM2BV. They are considered as sulfate resistant cement, and SEM3A, SEM3A that we don't have. Also, if I take two countries like Portugal or like Switzerland, okay, they have BM as sulfate resistance, and in Portugal they have almost most of a lot of product like limestone cement, the BM cement, the V cement. They have most of them because they go again performance based international standard. as a conclusion, I mean, I already somehow mentioned what was really important between this international standard. I would say over what I have seen, having been in this industry for more than 2 decades now, okay, over the past, I would say 2 decades, all international and national standards have introduced more performance-based specifications and supported by a joint effort from academia and from industry. You see a lot of collaboration, and this is what we want now to do in Sri Lanka. We want with the eye to eye to further push the limit for Sri Lanka. We want to really collaborate together and to bring more of this performance-based specification, okay, to fully take advantage of any advanced technology that happen out of our island. Second, from a prescriptive point of view, when you look to all these standards, you can feel that it is different to compare. As I say, it's apple, but one is red, one is green, you know. It's difficult to compare the ISTM and the EN standard products, just because from both the chemical and physical requirement, as test methods are different. Sand, they use Ottawa sand, very fine sand. EN, they use graded sand, 2 millimeter. Water cement ratio is not the same, Q, Priest, and so on. Difficult. However, what is important to mention, because we are talking about product here, okay? However, both standards have similar product composition and attributes. In both standards, you will see general use, special application, moderate heat, moderate sulfate, low heat, low sulfate. You will see all same attribute, okay? And due to the need and commitment on sustainable solution, what I see, and if you look at the statistic, development have moved all continents. The need and commitment on sustainable solution development have moved all continents. You can look all continents. If you look, sales of product in the market cement, without any exception, blended cement share is over 75%. If I just look my company in Sri Lanka, we are, as mentioned by Jan, we are above 80%. Okay, we are equal to international standard already in our product portfolio. And another conclusion, if I can say it, that in Sri Lanka, we should really consider adopting the BICN 197/1 as a whole, not just take part of it. To support, I may say, investment. Yes, to support investment. You see, now there is a new trend. It is a mega trend. We talk about well-being, we talk about digital. Now there is a virus trend, this is Corona. This is a big challenge that every rupee we will send it out of the country has to be counted. You agree with me? And that is very important. Even though here in Europe, they are starting, okay, for some strategic industry to nationalize. Okay, therefore we need to support what I call not any investment, but wealthy investment. That bring wealth to the country in terms of employment, in terms of innovation. Okay, that is very important. And offer sustainable and optimal solution. For the construction industry. Therefore, as I always said, take me out of the box and let me fly. That is really is innovation. And when I look all the youngsters, all the best engineers from the best university in Sri Lanka, they need this. They need this because they will challenge us. I'm 100% sure. I can see it in my team even. And in doing so, the following benefit can be captured and compared to benchmark countries such as Singapore, United Kingdom, Australia. Why I should always say, look what Dubai is doing, what Singapore is doing, what Australia is doing. We can do the same. Therefore, we can set the standards. We can also set our standard, reducing, for example, CO2 footprint and meet high sustainability standard with competitive advantage. When I have to soon start to bring product and pay 20 euro per ton of CO2, that is embedded CO2, I would prefer to develop my own natural resources in Sri Lanka and save this $20, for example. Reduce mix design cost, what I call cement utility factors. Very often I can see that people just continuously add more cement to optimize. Therefore, what is your kilogram of cement per megapascal? That is important. Therefore, you need to give flexibility. Offer more fixed solution for mass concreting in hot weather. I just put this hot weather because I can see huge potential to bring some other product to the market, to make much easier our concrete producer to develop low heat concrete without having to put ice on the aggregate, chill water, ice glass, ice crystal. That is costly. It costs us money, and there is technology to overcome this. And this is all money that is just spent like that we can really save. Improve the packing density for high stable, because a lot of complaint in the market regarding bleeding, segregation, problem of any problem in the fresh concrete for workable and pumpable mix over 3 hours. Sri Lanka is a high-end market. Sri Lanka is not Singapore. Singapore, they will never transport concrete more than even 2 hours. I look in Sri Lanka, very challenging market where we have to keep workability, where we use state-of-the-art admixtures, where the slump will increase with slump keepers. Yes, we have great technology for that. This is why it's very important to open up and to give more flexibility when it comes to cement standards. Last but not least, more flexibility with mix design optimization to fulfill the severe exposure condition. Yes, severe exposure condition. That is mitigate threat, okay, and assure high durability and design service life according to expectation. Okay, I end my presentation here, and I would like to really thank you. I don't know, I was not looking too much to my watch. I hope that I could bring you some valuable information for the topic of cement standard, and I will more than happy to answer for any question if I can, or the panel, okay, for what has been said. Thank you so much again. Thank you.
Thank you, Moussa, for your presentation, and I would like to apologize for all the participants. I think we have run out of a little bit more time than allocated for the presentation. Before we could start the panel discussion, we have, actually just want to introduce, we have for the panel discussion, Senior Professor Anura Nanayakara from University of Moratuwa, and Senior Professor Ranjit Disanayaka, Chairman of Civil Engineering Section Committee of IESL. And of course, Dr. Baalbaki will join us with Mr. Jan Kunik from INSI Cement N. So, Professor Nanayakara?
Yes.
Yes, okay, they're there.
You can hear me, I think, sir?
Yes, I can hear you, sir. So this question is for you.
Yes.
So if you look at the limited resources in the construction industry, such as fly ash and slag, and also simultaneously, we are talking about reducing construction cost.
Yes.
What could be our plan for the next 2 decades with regard to limited mineral components, and what could be our alternatives?
Yes, I mean, now if you look at the current trend in the construction industry, I think the engineers are taking more safe approach, I suppose. Now the whole problem is there. So I think Dr. Moussa said that, I mean, we are going for very high slump as well as very long slump retention. I mean, it is a costly business. I mean, you have to go for such a long slump retention. And also when it comes to the margin, strength margin specified by most of the consultant or the contract documents, this is a very high margin. So that cost, I mean, you have to add more cement and more admixtures. So that is where that, I mean, we can reduce the cost and save our natural resources. We have to be more conscious about the amount of cement that we are using and use supplementary cementitious material and reduce the clinker content and come up with a more durable concrete. That is the most important one. I mean, at the same time, you reduce the cost and you come up with a more durable concrete. So I think engineers must think about the cost of the production and when it comes to specification. So you should not over specify. That is the I think most important thing. I think people tend to over specify because they are afraid of failures. They are afraid of failure. So I think if you work on that line, I think you can reduce the cost to a great extent. Right? That is my brief answer for that one. We can go on talking about that one in detail. Yes.
Okay. Thank you, Professor. Also, I think I have a question for Professor Ranjit.
Yes.
Yes. Okay. So, so we just actually had a poll at the beginning of the session, sir, where we actually asked about the construction industry, whether we will be back to the normal, when we will be back to normal. So I think out of all the results, 89% actually said within 2020, end 2020. So there was like 42% said by in June, 47 said by December, that we'll be back to normal. So from a policy framework, and also since you hold a position of a secretary to the Ministry of Urban Development, I want to direct this question because if you look at it, blended hydraulic cement is well utilized and accepted in countries such as Singapore and Australia. But still Sri Lanka is more like OPC dominated in the market. While we see a lot of benefits, why we are delaying in applying in small scale into the mass market is what our question is to you.
Okay, the question is why not blended cement, right?
More or less,
okay.
Yes.
Yes, okay. Actually, blended cement is a greener cement. We being the Green Building Council of Sri Lanka, we always promote the cement or any product which are greener. So it is, you know that we established Green Building Council of Sri Lanka about 10 years before. Still we working on how to bring it to the policy level and various other aspects. So I see a little bit delay in happening things, but we never think about it is a delay line, but we have keep on educate the professionals and so forth. So even we had a meeting today morning also, we should talk in the sense which everybody, including the professional and the common man, understand what we are talking about. Likewise, I think we, being the professional, we have a bigger role to educate the people who understand this, the sense they can understand better way. Therefore, there is a delay, but still we have to keep on doing. I remember that at the beginning, this Portland cement was introduced by the at that time Holcim. I think my student Tushar was there working there, and Tushar asked me to help in order to promote the product. I remember that how far we went and educate the people around the country in order to promote the blended cement. Therefore, we have to keep on educating the people of the merit of the cement and how greener it is and so forth. This is where the point is there. Other than that, just just talking about the standard and various other things will not work. We have to give the merit, and it is a merit in terms of money and rupees and cents, as well as the environment and social and so forth. We have to educate the people. This is, thank you.
Okay. Thank you, sir. Dr. Baalbaki?
Yes.
Yes. So we had actually selected few questions from the Q&A which we had. So this one question is actually coming to you on the subject matter. What factors do you consider when developing a suitable cement type to Sri Lanka out of the whole cement domain available in the world?
I miss your question, Gayani.
Okay, let me read it out to you again. What factors do you consider when developing a suitable cement type to Sri Lanka
for the Sri Lankan environment?
Yeah, out of the whole cement domain available in the world.
Yes, I mean, okay, for Sri Lanka, you know, I always go with exposure condition. Okay, we have one of the best activator tip for us is heat. And we know very well that what cement best activator is heat. This is one factor that is very, I say, positive for Sri Lanka. Another thing is we are an island. We are also facing some severe environment, especially coming on the development in the coastal area. Therefore, I'm talking about here marine chloride coming from the sea. Okay. Therefore, first of all, I would say I will really definitely get out of the OPC thinking for two main reasons, really for two main reasons. OPC is too reactive for hot weather concreting first, and OPC in terms of flexibility, as we have in the market in Sri Lanka, still to import product, very difficult to assure, okay, quality consistency of those products when we have to fulfill, for example, C3A requirement for sulfate that is not anymore, that is important to mention, that a lot of people confuse. You see, when I'm talking about a moderate sulfate resistance, it is not the cement to consider for marine structure. Huh? If you look all the standards, it is not allowed to use a high sulfate resistant cement in the marine environment. This is why the solution is to get out totally from OPC mindset, go to blended cement as the 595, as the 1157 is doing today, and they have plenty of more than 3 decades of experience, okay, with composite cement where you have slag, fly ash, multiple blend, and this is where Sri Lanka we should go. Because again, when I'm talking about cement utility factor, we should not forget that 60% of material cost is coming from the cement. This is first things. And for us in Sri Lanka, out of the 5-6 million tons of cement we need every year, okay, we have to import. Therefore, how to better use our better resources is to go to our more sustainable development, okay? And therefore, to close this, we need to see a totally different and blend cement. That is for me the cement form what I see in Sri Lanka.
Thank you, Moussa. I just want to quickly come back to the recovery period post-COVID and the results. So 40% of the respondents said until June we will recover from COVID and the impact on the construction industry. I think that are very optimistic results. I hope it as well, but I think it's very optimistic. Another 40% until the end of December of this year, and another 10 to 15% expect the full recovery until Q1 next year. So I think it will end or it will last until 2020, the recovery, especially from the government side, there are significant outstandings to many developers and contractors, and I think that's where the government and policymakers must do payments and address that. But I'm sure it's at the table of the respective government people. Professor Nanakaria, Professor Desanayake, thank you for joining also our meeting today. Thanks for your support. I think over the last 2 years we have done significant impact to sustainable construction and a significant increase in the share of total blended cement used in the country. And we've saved many trees and many resources with that. I think it's also going through all the universities today, and I thank you for your support there. If we look at the policy framework, Professor Ranjit, how do you see the policy framework shaping up for the post-COVID crisis on an economical level for the construction industry? Do you have any insights from your urban development ministry on how many projects will actually continue at the same speed once the markets are open and curfews lifted again?
Yeah, let me say this way. For example, the fully recovery is still not guaranteed. I think if you go lockdown of the country, but because of the health reason, but the consequence of coming as an economic problem will be more severe. So I don't have to explain it. I think everybody understands. If you go like this one, there will be a different kind of problem within the country. The poor are getting poor and poor. Then social problem will be a most critical issues that may come in future. Therefore, I believe whether we completely recover from the control the corona or not, we may have to open up the country very soon. Maybe in this situation, we will have to live with the corona. So that now I think this is in a way we kind of try to control it. We could control it up to a certain level, but again, situation was changed after the finding of the army personnel contact with the virus. But I think once we government identify the roots of that also, I think we have to open up the economy very soon. Actually speaking, regarding the construction industry, government is really wanted to open it during last 1 year and so. But whenever they try to wanted to open it, there are different situation comes. Here I think we have to always, it is a medical situation. We have to get the opinion of the medical personnel. But again, but when we listen to it, but again, the day by day, the economical problem becomes as I always mentioned, that the biggest challenge that we are facing right now, continuation of the business. That is a critical issue. So in order to do that, of course, we have to find out the short-term and long-term solution. And being the construction industry, there almost every corner of the country, people are directly or indirectly engaging. Therefore, opening of construction industry is one of the best industry that we can open right now. Again, we have to look after each and every site. They are controlling measures. Of course, that has been developed by the WHO and many, even we have some guidelines locally. Therefore, my belief is that sooner or later, country will open, especially construction industry will open very soon, at least within a month. But maybe we are thinking here that nobody can say the corona will end of this year. It might be here in the world another 2 years or 3 years, and sometime we may have to live with the corona. Therefore, now we have to we have to train to live with the corona, so that we cannot go being closed the economy. Therefore, we will have to open the economy very soon. I believe that it will operate like almost like the 70% like end of the May as we had before. Therefore, I think the construction in the then even right now, actually, I've been working in the directly construction industry. We have opened up our construction. We have the 3 sites in Kandy we open. But what are the problems that we are right now facing? When we send the lorries to bring the sand, there's a barriers so that they will not allow our lorries to cross the district. So that they ask us to bring the certificate from the various authorities, health inspectors and so forth. So, but when they formalize this, still the problem is the construction site can be open. The material flow in is not happening right now. So these are the small issues that once it is open, I think I believe that the end of May and July, at least the construction will go up to the 70%. Therefore, you also get ready for the supply the cement to the market. This is what I believe.
But thank you, Ranjit, and I agree. First, the social impact must be feathered, and once that's solved, the rest will come up as well, including the economy.
I believe this time is we are getting trained to how to live with the corona. Now people are little bit trained to live with the corona. So we have to live with the corona.
Thank you.
And it's a good time for the country like Sri Lanka. We have to think about our own economic model rather than depend on the more and import and so forth. We have to think about our own innovative economic model where whatever they produce in this country must produce and again we have to be self-sustained in agriculture and so forth. This is a good time for a country to have the different mindset and model, and because this time even everybody cooperate, so that this we have to get the blessing to the government, and we can implement a lot of things like why not we import many things that we could have produced in this country. There are different kind of mafias and here and there. Before, right now, these people cannot act as earlier. Therefore, that is a blessing for the country and convert the whole economy to an innovative economic model and go for the self-sustainability wherever possible. I don't say that we should go for the completely shut down economy and produce everything within this country. No way that you can't do it. But wherever possible, we must go for the our own economy, innovative economy. We must go for the more and more research and bring the product out of our country and go for the investment.
Thank you.
Thank you. So this question actually goes to Professor Nanakara. So this is coming from one of the participants. For complete hydration of cement requires at least 0.3 water cement as per the shown slides by Dr. Baalbaki. But in the Sri Lankan currently, we use between around 0.24 to 0.35 water cement for high strength concrete. In this situation, can we expect the fully completed hydration process?
Yes, so if it is less than a minimum requirement, definitely not. I mean, the entire thing will not hydrate. So some of these cement particles, contribute to the more dense structure, right? It is acting like, ultrafine particles in the cement matrix. And it is not necessary for the entire cement to be fully hydrated, right? So that is why even with 0.2 water cement ratio, I mean between 0.2 and 0.3, we are getting very high strength concrete. It is that entire thing should be get hydrated. So if it is fully packed and it is if all the pores are filled, then I mean you can get the high strength concrete. That is why less than the minimum cement water cement ratio required for the full hydration, we are getting very high strength. I mean, it won't happen. I mean, the entire cement will not hydrate, even in high strength concrete.
Thank you, sir. I think we have a very limited time allocation for Q&A. Before we actually close the session, I actually invite Engineer Nandana Amanatudua, General Manager, Industrial and Sales of INSI Cement, to give the vote of thanks for today's session.
Thank you, Gani. Good evening, everyone. Thank you very much for being with us for this first eye-to-eye webinar session for the last 2 hours. We successfully completed the first session of this part 2 webinar on overview of international cement standards for performance-based specification organized by INSI. Even though the prevailing situation is not favorable, we believe that it is our duty to support to keep the same momentum with shared knowledge and experience and exposure to the industry. So my warm gratitude goes to Dr. Moussa Baalbaki for conducting the session today and his continuous effort to contribute maximum to the fraternity through innovation to industry collaborative space. Further, I will like to extend my sincere gratitude to Professor Nanayaka and Professor Anjit Disanayaka for being a panelist for this our first ever webinar session. And special thank goes to our valued stakeholders who join us today in this webinar and being with here for the 2 hours or more. And we hope you all will join for our second webinar also. Further, let me thank our colleagues at INSI who supported to organize this webinar with all the hard work they have done behind the scene. Further, we will come back to you. We as a team here try to answer all the Q&A questions which they raised during the session. So if you have missed something, definitely we will come back to you with the results. Before I end up, let me remind you to be safe and conscious on all the possible avenues of COVID-19 and be safe. And thank you very much. And always be with us, be with INSI. Thank you very much. And see you soon with the second stage.
Thank you, Nandana. Just wanted to remind everybody there will be a feedback form which will be sent you via Zoom as well as on text message. So please give your valuable feedback because that will be something that we could look at for our next session, which we hopefully could have next month. So
thank you very much, everyone.
Thank you.